mere idle concept. In the phraseology which Bacon applied to the doctrine of final causes, it is a barren virgin. Nothing is deduced from it, and the ether merely subserves the purpose of satisfying the demands of the materialistic theory. The important concept is that of the shifting facts of the fields of force. This is the concept of an ether of events, which should be substituted for that of a material ether. It requires no illustration to assure you that an event is a complex fact, and the relations between two events form an almost impenetrable maze. The clue discovered by the common sense of mankind and systematically utilized in science is what I have elsewhere (cf. Organisation of Thought) called the law of convergence to simplicity by diminution of extent. If A and B are two events, and A1 is part of A and B1 is part of B, then in many respects the relations between the parts A1 and B1 will be simpler than the relations between A and B. This is the principle which presides over all attempts at exact observation. The first outcome of the systematic use of this law has been the formulation of the abstract concepts of time and space. In the previous lecture I sketched how the principle was applied to obtain the time series. I now proceed to consider how the spatial entities are obtained by the same method. The systematic procedure is identical in principle in both cases, and I have called the general type of procedure the method of extensive abstraction. You will remember that in my last lecture I defined the concept of an abstractive set of durations. This definition can be extended so as to apply to any events, limited events as well as durations. The only change that is required is the substitution of the word event for the word duration. Accordingly, an abstractive set of events is any set of events which possesses the two properties: 1, of any two members of the set one contains the other as a part, and 2, there is no event which is a common part of every member of the set. Such a set, you will remember, has the properties of the Chinese toy, which is a nest of boxes one within the other, with the difference that the toy has a smallest box, while the abstractive class has neither a smallest event, nor does it converge to a limiting event which is not a member of the set. Thus, so far as the abstractive sets of events are concerned, an abstractive set converges to nothing. There is the set with its members growing indefinitely smaller and smaller as we proceed in thought towards the smaller end of the series, but there is no absolute minimum of any sort which is finally reached. In fact, the set is just itself, and indicates nothing else in the way of events except itself. But each event has an intrinsic character in the way of being a situation of objects, and of having parts which are situations of objects, and, to state the matter more generally, in the way of being a field of the life of nature. This character can be defined by quantitative expressions expressing relations between various quantities intrinsic to the event, or between such quantities and other quantities intrinsic to other events. In the case of events of considerable spatiotemporal extension, this set of quantitative expressions is of bewildering complexity. If E be an event, let us denote by Q times E the set of quantitative expressions defining its character, including its connections with the rest of nature. Let E1, E2, E3, etc. be an abstractive set, the numbers being so arranged that each member such as En extends over all the succeeding numbers such as En plus 1, En plus 2, and so on. Then corresponding to the series E1, E2, E3, En plus 1, there is the series Q, times E1, Q times E2, Q times E3, Q times En, Q times En plus 1. Call the series of events S and the series of quantitative expressions Q times S. The series S has no last term and no events which are contained in every member of the series. Accordingly, the series of events converges to nothing. It is just itself. Also, the series Q times S has no last term. But the set of homologous quantities running through the various terms of the series do converge to definite limits. For example, if Q1 be a quantitative measurement found in Q times E1, and Q2 the homologue of Q1 to be found in Q times E2, and Q3 the homologue to Q1 and Q2 to be found in Q times E3, and so on, then the series Q1, Q2, Q3, Qn plus 1, though it has no last term, does in general converge to a definite limit. Accordingly, there is a class of limits, L times S, which is the class of the limits of those members of Q times En, which have homologues throughout the series Qs as n indefinitely increases. We can represent this statement diagrammatically by using an arrow to mean converges to. Then E1, E2, E3, En plus 1 converges to nothing, and Q times E1, Q times E2, Q times E3, Q times En, Q times En plus 1 converges to L times S. The mutual relations between the limits in the set L times S, and also between these limits and the limits in other sets L times S1, L times S2, which arise from other abstractive sets S1, S2, etc., have a peculiar simplicity. Thus the set S does indicate an ideal simplicity of natural relations, though this simplicity is not the character of any actual event in S. We can make an approximation to such a simplicity which, as estimated numerically, is as close as we like by considering an event which is far enough down the series towards the small end. It will be noted that it is the infinite series as it stretches away in unending succession towards the small end which is of importance. The arbitrarily large event with which the series starts has no importance at all. We can arbitrarily exclude any set of events at the big end of an abstractive set without the loss of any important property to the set as thus modified. I call the limiting character of natural relations which is indicated by an abstractive set the intrinsic character of the set. Also the properties connected with the relation of whole and part as concerning its members, by which an abstractive set is defined together, form what I call its extrinsic character. The fact that the extrinsic character of an abstractive set determines a definite intrinsic character is the reason of the importance of the precise concepts of space and time. This emergence of a definite intrinsic character from an abstractive set is the precise meaning of the law of convergence. For example, we see a train approaching during a minute. The event which is the life of nature within that train during the minute is of great complexity, and the expression of its relations and of the ingredients of its character baffles us. If we take 1 second of that minute, the more limited event which is thus obtained is simpler in respect to its ingredients, and shorter times, such as a tenth of that second, or 100th, or 1,000th, so long as we have a definite rule giving a definite succession of diminishing events, give events whose ingredient characters converge to the ideal simplicity